All right, here's 642. We'll start with a little formula involving the dot product. Remember, section 4 is all about the dot product. I'm going to sketch these two vectors, and the goal here is going to be to identify the angle in between them. Hopefully we have enough room here to do this. I have vector u, which is 3, 1, 2, 3, 4, whoops, 5. Kind of cutting off v here a little bit, but that's okay. And 1, 2, 3, 4, 1, 2, 3. There's vector v. The angle that this formula is referring to is theta, right there. Okay? Using a calculation that involves a dot product, we can get what that angle is. In a lot of physics problems that involve vectors, that angle can be a very relevant piece of information that you would want to know. Okay? Here's how it would look. The formula is fairly straightforward. What it will get us is this angle's cosine value. Now right off the bat here, as I'm looking at our diagram, I'm kind of thinking about what theta is. I don't know. It obviously looks significantly less than 90 degrees. Looks less than 45 as well. I don't know, maybe 20, 30? So it looks relatively small. Okay, but on the top of our formula, we'll have the dot product, which would be 3 times 4 plus 5 times 3. And then on the bottom, we have the product of both of these vectors' magnitudes. Okay, for u, that would be the square root of 3 squared plus 5 squared. And then for v, that would be 4 squared plus 3 squared. Okay? Eventually, we're headed towards our calculator for an inverse cosine. But in the meantime, there's a little simplifying to be done. I mean, I wouldn't throw it all in like that, because that's going to be really easy to make a mistake. I wanted to get something that's easier to put in. Top simplifies to 27. That, again, is the dot product of the vectors. The magnitude of u is the square root of 34. The magnitude of v is the square root of 25. And this will get us 27 over the square root of 34 times 5. That I would take to my calculator. You know, that as long as I put parentheses around the bottom of that square root of 34 times 5. That looks good. Now, I wouldn't go to a decimal approximation, but I just want to double check here. This is a cosine value, so if I got something that was over 1, that would be a problem, and the cosine inverse isn't going to work. But we don't. Inverse cosine of 0.926 is about 22.17 degrees. Okay, about 22.17. Which, if we relate that back to our diagram, seems consistent. That looks to be somewhere in the ballpark of about a 22-degree angle. All right, I'm going to go back to the unit circle here for a minute and just talk about cosine. Right, this formula that we've seen here for dot product obviously involves cosine. Okay. Specifically, just really two angles. If we were talking 0 degrees, that location at the unit circle was 0, 1. And therefore we would say that the cosine of 0 degrees is 1. The one I really want to focus on here is 90 degrees. There, that is, whoops. I gotta go back to right here. You were probably looking at that saying, yeah, not true. That point would be 1, 0, because again I'm looking at my x-coordinate, 0, 1. Right now we're talking about 90 degrees. Okay, this is just a refresher. I mean, you're probably looking at this saying, yeah, I know, not to mention I have a copy of the unit circle in my notes. I'm just getting towards this, that we're okay with the idea that the cosine of a 90-degree angle is 0. I've seen that 100 times, but quick refresher. Okay? So if we go back to our formula with this piece of information, okay, that the cosine of an angle formed by two vectors is u dot v over the magnitude of u times the magnitude of v. Okay? Now, let's say if this whole thing were to equal 0, remember this gives us a cosine value. If that whole thing were 0, what would that imply about angle theta? Means that theta would be 90 degrees. Okay? Now look at the structure of this formula. Okay? And if you really think about it, for that whole thing to equal 0, the bottom, like the product of the magnitudes, doesn't really matter. Okay? The whole thing is going to be 0 if the dot product is 0. Right? If there's a 0 on top of that fraction, what do the magnitudes matter on the bottom? That whole answer is going to be 0, which means when we do the inverse cosine, theta will be 90 degrees. Okay? So this has to do with kind of a specific case that we check. All right? New term here. You've probably noticed a vector sometimes kind of has its own terminology. You know that like a constant number we call a scalar. So for orthogonal, think 90 degrees. It's very, very similar to perpendicular. It's got a few differences that don't necessarily pertain to us. If you just think of orthogonal like perpendicular, you will be okay. That's a perfectly fine way to remember it. If you go farther on with vectors, you'll get some obscure properties where two vectors being orthogonal isn't exactly the same as being perpendicular, but whatever. Here's what it means for us, though, is that if we have two vectors and we check their dot product and it's 0, you've got two vectors that are orthogonal, that they form a 90-degree angle. Okay? So I've got u and v down here, just a regular old dot product. 2 times 6 plus negative 3 times 4. That is 12 plus negative 12. So to answer this question, are those vectors orthogonal? As soon as we see that the dot product between them is 0, we would say yes. Now I don't have another example on it here, but if the dot product wasn't 0, would we then jump to the conclusion that they are not orthogonal? And the answer there is yes as well. Okay? The only way that we can justify that two vectors are orthogonal is to see that that dot product is 0.